Hello class, this is Mrs. Gallegos, and today we are going to discuss ionic bonding. This is topic 4 and this is section 1, first video in section 1. So the first question we're going to ask ourselves is, how are ionic bonds formed? Ionic bonds are always formed between a metal and a non-metal. The metal, as you know, because they have very low electronegativities, are more likely to lose electrons and become oxidized. And when they do, they become cations. On the other hand, the non-metals, which have very high electronegativities, are more likely to be reduced, gain electrons, and become anions. And so ionic bonds are formed by electron transfer, when the electron is transferred from the metal to the non-metal. Our next question is, what is the driving force behind forming ionic bonds in the first place? Well, we know that an octet of valence electrons means stability. And these 8 valence electrons are also known as a noble gas configuration. So if we anthropomorphize the atom, they all love to have they are jealous of a noble gas configuration. So if we take sodium, which has the configuration neon plus 1 electron and a 2s orbital, the easiest way that it can have an octet is to lose its 1 valence electron, and then it will have the configuration of neon and be a +1 ion. As we know, all the elements want to be a noble gas like neon. Next, if we take chlorine, which is on the right-hand side of the periodic table where the electronegativity is higher, we understand that because chlorine has neon's configuration plus 7 valence electrons in the second period, and all it needs is just 1 more valence electron to have the noble gas configuration of argon. And so the driving force behind ion formation is for those elements to achieve a noble gas configuration. And so, like neon, we call the noble gases that because they do not have any driving force to form ions because they are already full. They already have the noble gas configuration. So if we look at, after ions are formed, what does an ionic compound actually look like? So we see that ionic compounds form an ionic lattice. And if you look lithium in yellow, chlorine in green, you'll see every lithium is completely surrounded by chlorines, and every chlorine is completely surrounded by lithiums. And that's because we have an electrostatic attraction between the positive and the negatives. And they form these very rigid structures with great forces of attraction between them called the ionic lattice. Now right here is one formula unit in an ionic lattice. I could describe the formula of this ionic substance as lithium 30, chlorine 30, but we always, because there's no really discrete molecule here, and so ionic compounds don't form molecules, they form these ionic lattices. And so their formula is always the lowest ratio between the 2 ions. So in this case, it's LiCl, or lithium chloride. Remember that the force of attraction between the 2 ions is described by Coulombic attraction, where E, or the force of attraction, is equal to the 2 charges of the ions divided by the distance between them. So if we look at trends, then we see that as you move to higher charges, that the force of attraction increases. And then if the ions are smaller, which means the distance between them is less, you'll also have a greater force of attraction, and that affects the lattice. The lattice is a much stronger lattice if the charge of the ions is greater or the radius is smaller. So let's look at what that means as far as energy. So we can describe lattice energy, and lattice energy is, as you see on the bottom, the amount of energy it takes to completely take the lattice apart. So if I look at the lattice energy of an ionic compound made out of sodium and fluorine, I see that that lattice energy is 910 kilojoules. So 910 kilojoules of energy will be released when I take apart 1 mole of sodium fluoride lattice. And so if I look at another compound, calcium oxide, where the ions are both 2 plus and 2 minus, which means that by Coulombic attraction, the force of attraction will be much greater, so the energy that's released is much greater also. So this lattice is held together with a greater force of attraction, so it will release more energy. It takes more energy to decompose the lattice. So if we look at other ionic substances, we can see the same trend. So if you go across the first row of the table, lithium fluoride, fluoride is the smallest of the halogens, and so here we see the lattice energy is the greatest. But as the halogens get larger and we don't change the negative charge, then we see the lattice energy go down. What happens if we pair lithium with oxygen, which is -2? Well, now we have a much greater magnitude of charge. We have -2 times 1. And so we see that the lattice energy is greater, so we know that that crystal is held much more tightly together. But as you see, all of the ionic substances have very large lattice energies, which means that force of attraction is very great in an ionic compound. So how does this force of attraction explain some of the physical properties that we see? Well, the first thing we know about ionic compounds is they have high boiling and melting points, and that makes sense to us. So as you see, again, sodium iodide, when they're both +1, -1, we have a melting point of 660 degrees Celsius. But if I go down to magnesium oxide, MgO, which is Mg +2, O2-, I have a much larger melting point. And that's directly related to that lattice energy. I know the lattice energy is much greater in magnesium oxide, therefore it takes more energy to change from a solid to a liquid state. So let's look at another property, something called volatility. Volatility is a liquid, its tendency to form a gas. And so we know if those particles in the lattice are held very tightly together, then we know that ionic substances have very low volatility. They're not likely to go from liquid to gas. So another property we can look at with the ionic substances is their ability to conduct electricity in the aqueous or the liquid state. So if you look at the middle diagram, which shows the ionic lattice, the light bulb isn't lit. This does not conduct electricity. However, if I dissolve this ionic substance in water, the water pulls the lattice apart, and now I have free moving charges, and as you can see, the light bulb lights. This also works if I take the solid lattice and turn it to liquid. Then again, I don't have a rigid lattice structure, but I have moving charges, and then a liquid ionic substance will also conduct electricity. The last property that we need to know is about solubility. And as you can see in this diagram, I have a beaker filled with salt, and the water, I don't know if you know this from your biology or your previous science experience, but water has positive and negative. And so you see the diagram, the little red and white molecules, there's 2 positives, those are the hydrogens, and a negative, that's the oxygen. And because water is charged and salt, which you can see the lattice crystal in the bottom left hand of the diagram, is also charged, the water can pull the lattice apart, and we call this dissolving. So now the ions are distributed amongst the water, and we call this dissolving. And so when we talk about solubility, we always have to remember the rule of thumb, like dissolves like. So if I am charged, I am dissolved by a solvent that is also charged. If I am not charged, then I am dissolved by a solvent that's not charged. And we'll talk about that further. So because ionic substances are soluble in water, we know that they're not soluble in nonpolar or non-charged solvents. And that is it for today's lecture. I'll see you in class when we next meet.